So we are now live. So welcome to this lecture. So we already mentioned this correlation and covariance and variance of sum. We'll talk about this. So there are several situations in which we want to assess a random sequence or set of random variables that form a vector, that we take a random vector. In this case, we talk about two variables, but often we have more than two, and you know, statistical analysis often discusses a high dimensionality in this situation. So we have very many random variables. All the theory that we apply here can be used with several variables, but of course, in these cases, the covariance, which we will define between two variables, well, there are generalizations thereof, but very often we only have pairwise covariance. So covariance is a measure of variance, mutual variance, if you will, of x and y. So we defined it as the expected value of whenever, I mean, you can consider it whenever we make a random experiment with that reveals us one particular instance of this random vector xy. And the covariance is the measure of the expected value of the product of the deviations or you know, how they relate to their respective expected values. So if the expected value of x is mu of x or mu x and expected value of y is mu y, then when we measure this random vector, we get a point xy. And this gives us the expected value of x's distance from its, or x's deviation from its expected value multiplied by y's deviation from its expected value. And intuitively, this is a measure of, the covariance is a measure of how they deviate or vary. So the variance is like a measure of how far from the expected values does a variable tend to go, and covariance is how these differences relate to one another when we measure them together. So if x and y, if y is big when x is big, and y is small when x is small on average, or you know, tends to be, then the covariance is positive. On the other hand, if x is small when y is big, or tends to be, and vice versa, then the covariance would be negative. And the covariance would be zero if there's no relation. And in fact, covariance will be zero when x and y are independent. There are, of course, situations where x and y are not independent, but the covariance is still zero. There are examples which we will discuss. But most importantly, to think that we usually assume that if the covariance is zero, then they're pretty much independent. But that's a dangerous assumption. We'll discuss this later a little bit. So we define this, and we can define the covariance of x and y simply by taking the expected value of x times y minus the expected value of x times the expected value of y. Now, this may or may not be helpful intuitively, this theorem, in the sense that you can think that if we take x and y, we take their product, and the expected value of their product is bigger than the product of their expected values, then the covariance is positive. This means that basically that the negative values, if you think, I mean, intuitively think that the expected values are close to zero, then the negative values tend to stick together, and when we multiply x and y, we actually get a positive value usually, and the covariance is positive. This can be proven by the expected values linearity, so it's fairly easy to calculate from the covariance directly. And also, this is a nice also in that in this formula in theorem 3.18, you see nicely the fact that if they are independent, then the expected value of x, y is in fact equal to the expected value of x times the expected value of y. So this covariance is definitely zero when they are independent. Like I said, converse is not true. There are several cases, not even pathological, mind you, but there's several cases where there is the converse is not true. So there are situations where covariance may be zero, but so here was an example of the unit circle. So if you take the unit circle, so assume that we are randomly picking points on the edge of the unit disk, so on the unit circle. If we calculate their covariance of x and y component, it will be zero. It's fairly easy to see because if you take a random point and you have the x value is determined, then the y value for that is determined to be something or the negative of that, but it's equally likely to be positive or negative. So this means that it's the covariance will be zero. This is just an intuitive intuitive explanation. I'll show you during the lectures or the exercise sessions a little bit of this, how you can prove this. Right. So the covariance measures only linear dependence, so tendency to fall in line, maybe you want to do like this. Here we define what is known as correlation. So if we take the square root of the variance of x and the square root of variance of y, let's call these the standard deviations of x and y. And here, like I said, I didn't fix this yet, but here that should be y. You normalize the variables by dividing them with their standard deviation. What you end up with is two variables that have variance 1. So these newly defined variables have variance 1. Now, if we use this then to define this thing called we calculate the covariance of these normalized variables, and we can think of this. We end up with the correlation of x and y, and it's defined as the covariance of x and y divided by the product of their standard deviations, or alternatively the square root of the product of their variances. This is called the linear correlation. So correlation is often used when we talk about some things being correlated. So a correlation, not the only thing, but I mean, what it says really, correlation really says is if it's positive, it says that the values tend to be high or low together, with regards to their expected values. So there is, for instance, there is a high correlation between weight and height of people, because taller people tend to weigh more on average. So if correlation, like in this situation, correlation is it's a direct physical relation, because bigger people tend to be both taller and heavier. Just you have a lot more bone mass and more pretty much anything in your body, then you weight more. There is also a correlation if you take the monthly ice cream consumption in Finland and how many people get die or get seriously injured in boating related and swimming accidents. So why is there a correlation? Well, there's a correlation because the lakes are frozen most of the year, not most of the year, but I mean, whenever it's cold, and in the warmer months, people tend to eat more ice cream. So there's definitely no direct reason why they are correlated, but there is a definite positive correlation. There's actually a web page, you can look it up. I don't recall what it's called. I think it's called Spurious Correlations or something like this. There are all kinds of these ridiculous correlations that you can find in certain time frames, like the number of movies Nicolas Cage has appeared in, and then the number of people who died by asphyxiation or something like this. So there can be positive correlations, obviously, from data that are just ridiculous. This correlation here is correlation within the model. So this is not something that is calculated from data, but we'll see how we use this interchangeably. But in this case, there are two concepts of correlation. There is one where we measure things in the real world with random variables. We'll talk about that shortly. But this is just a theoretical concept of correlation. So there's covariance of x, y divided by the square root of the product of the variances. So we'll talk about this. We'll see this shortly. So what does the correlation mean? We can calculate in this previous example, for instance, we had established the product in this example of f, x, and y, where we had this triangle in which we had this density function of xy, and we calculated, established that the expected value of x times y is 4/9. We can calculate the expected value of x and the expected value of y, and we can calculate their covariance, and it turns out that it's 4/225. So it's minor, it's small, but it's positive. And then when we have the variances calculated, I'm not going to show you how it's done. I mean, we can calculate it by simple calculus here. We calculate the variances of x and y, and we can calculate the correlation. It's 0.49. So there's definitely a correlation that is positive, but it's not huge. So these can be easily proven when we have the correlation. The correlation will always be between -1 and 1. We can prove this fairly easily by looking at the formula. The correlation of x with itself is always 1, and the correlation of x and minus x is always -1. If the covariance is anything, if there is anything other than perfect correlation, then x and y are not in complete linear relationship. So the correlation of x and y has absolute value 1. It may be -1 or +1, if and only if the probability that y is equal to ax plus b is equal to 1 for some a and b. So in fact, so that this is a bit badly said, it's 1 if and only if there exists a and b such that the probability that y is equal to ax plus b is equal to 1. And the sign of a, so if a is negative, then the correlation is -1. If a is positive, the correlation is 1. The only exception to this is, of course, a being equal to 0, in which case if a is equal to 0, then, well, y is just equal to b, and this is not the case. So even if the correlation of x and y is 0, it doesn't mean that there isn't a dependency. So if we have, for example, we have two variables, two random variables x and y, such that x squared plus y squared is equal to 1. We can show that this is the square, the circle example. If we have different kind of correlations and we make these gather data of x and y, then I'll annotate this a little bit. I hope you can see this now shortly. Let me see. So the situation is this, that if we think of, let's assume that roughly, I mean, it's not quite, but let's say that that's the expected value of X. This is the expected value of Y. And you can get a rough idea. And again, I'm not saying that this is the way you calculate, but you can get a rough idea that there is a positive correlation by seeing that there are in this region and in this region, I mark this with plus, in both, there are more in these this upper left and upper right and lower left quadrants when you draw these lines with the expected value than there are in this upper left and lower right. So in this case, the correlation seems to be positive. And in this case, there is a surplus here and here, and there is less points here and here. So in this case, the correlation seems to be negative. In this situation, assuming that's roughly where the, so if we do that, then there's actually nothing, there are no points, 0 points here. There are 0 points here. So this is in this case, the correlation is -1. But here, if we, this situation might be such that, well, that's not smack in the middle, but right. So in this case, we'd have equal amounts in all of these quadrants. And I mean, it's not in this case, but if there's a roughly equal amounts in all of these quadrants, then in this case, this correlation seems to be 0. Whereas there is clearly a dependency between those two, right? So correlation doesn't reveal even all the obvious dependencies, but it does reveal these kind of linear dependencies, so that if you try to fit a line, then that line clearly has a negative or a positive slope, then we have negative or positive correlation. And then, you know, if everything falls in line, then the correlation is either -1 or 1. A more accurate analysis of linear dependencies and between multiple variables as well can be done using regression analysis. So why this is just an introductory course to statistical analysis and statistical inference, then we're not going to discuss regression analysis in this course. But it's definitely something that should be something that you study if you are going to study, you know, statistical inference. Then regression analysis, I think, is the next go-to thing after this course. Any course that contains regression analysis would be highly recommended. All right. Let's move along. So here's a theorem that says basically that if you have two variables, X and Y, and then you're looking at the variance of what happens when you take some X and some Y, let's say AX plus BY. So perhaps the easiest way to think about this is to think about A and B as being coefficients between 0 and 1, and their sum is 1. I mean, this is not necessarily the case. This holds for all A and B, but think about this in the following way. You are going to invest 1,000 euros or 1,000 something money. You're going to invest some amount of money, and you have at your disposal, you have a decision. How do you divide your investment between two different investment possibilities? Like, let's say X is, you know, you're going to buy some stocks, and Y is like something ridiculous. Let's say you're going to buy gold. It's not ridiculous, but you know. So you want to minimize your variance, meaning the risk of your investment. So you look for the covariance of X and Y. You know, what happens to gold and stocks. Sometimes they're not, the covariance is not, definitely it's not, probably not negative. It could be slightly negative, I'm not sure. But let's assume if it's negative, then what you get is you get this solution that, you know, if you put some percentage in stocks and some percentage in gold, you can minimize the variance by finding a suitable balance here using this theorem 3.22. So it's actually a really useful theorem. What does it say basically? It says basically that if you add two variables together, if they have a positive covariance, then the variances don't just add up. There's a variance component of X and variance component of Y. They behave just like the variances, but the variance is not additive unless the covariance is 0. If they are independent, look, if they are independent, then the variance is simply, you can take the variance of AX, add the variance of BY, nothing to it. Remember, the variance of AX is A squared times the variance of X. But then, because you're adding X and Y, then the variance of this is amplified by the fact if they have positive covariance, and it's diminished if they have negative covariance. Why? Well, if they have negative covariance, then when X is small, then Y tends to be big, and vice versa. So whenever these push the sum of X and Y towards the expected value of the sum. Whereas if they have a positive covariance, then whenever X is far away from its expected value and Y is also far away, it's usually in the same direction. So we are actually even further from the expected value of the sum, right? Than usual, than simply by the usual X and the usual Y. So in particular, only when X and Y are independent, then the variance of AX plus BY is going to be A squared times the variance of X plus B squared, the variance of Y. This is, again, the proof is fairly straightforward algebraic manipulation of the formula and use of the fact that expected value is linear. They're not going to need to go here in great depth or detail. But if a sequence of variables is independent, then their variances get added up in this quadratic manner. So here's another example. Let X and Y be random variable with variances of X is 2, the variance of Y is 4, and the covariance is -2. So let's define it as 3x minus 4y plus 8 has this variance, which is 130. So the variance becomes quite big. All right. There were not many examples here that are suitable for group work at this time, of which I'm a little bit sorry. This material wasn't designed for this internet course all that well, but there will be some later, and we'll have a go at some exercises in group work, so bear with me. There's one other thing that we need to discuss. These are more theoretical. Look, this section 3's things are more theoretical in nature. So we are going to be talking about some rather theoretical concepts here. Don't fret The idea here is to give you an in-depth idea of the nature of randomness before we venture into this short latter half of the course where we talk about the statistical analysis and random distributions. So Chebyshev's inequality, it's been the different transliterations of it. This, some use CH something, and I just copied this from somewhere, so it depends on how it's transliterated from Cyrillic alphabet. So the thing is, let's say that we know that we have a random variable. If we know its density function, we can compute the probability of any event. So when we say that some variable has a known distribution, then we can do anything, any calculation of computing its probability for any sorts of events. The situation is different, however, if we don't know the density function. We only know, for instance, some estimates of expected values and variances, but we don't know what the underlying distribution looks like. Because, the distribution's density function itself, if we think, let's think in terms of real numbers. So the density function can have various shapes, which cannot be reduced to just expected value and variance. But very, very often, this is the sort of information that we get. So we don't necessarily get a good scatter plot of data. Also, in modern day data analysis, that's actually often what we do get. We do get a lot of data. But let's say that for some reasons we have obtained only the expected values and variances regarding certain variables. And we don't know what distribution they come from. So the distribution can have different shapes. We have just a general idea of the center point of that distribution, which is given by mu, and the width, how wide it is, or how far does a random point fall from that center point, which is the measure of this is the variance. So we have these two measures. Because the variance tells us how far from the expected value the random value ends on average, or it contains some of this information. Then we might be able to assess the probabilities of certain events. For instance, how far do they fall from certain from the expected value? I mean, if we know the variance, I mean, how the more extreme the values, the less probable they tend to be. And the inequality called the Chebyshev's inequality, given in theorem 3.25, I really do hope that you understand. This is like the minimum standard. So the idea is that it can't get worse than this. So it says that the probability of getting a value larger than t, or further away than t from the expected value, is less than or equal to the variance squared over that t squared. What does it say? Alternatively, it says that the probability of landing closer to mu, or closer to the expected value than t, is is at least 1 minus the variance squared over t squared. So in particular, if we measure the distance from the expected value as multiples, you can think this k as being integer if you want, but it can be some other measure as well. If you consider them as multiples from the expected of the standard deviation, then the probability is bounded above by the inverse square of that multiple. So I don't know if you remember, some years ago they were hunting for the Higgs boson at the with the Large Hadron Collider, the LHC, and they were gathering lots of data, and they were looking for what they call I think it was called the 5 sigma event. This means that under the assumption that this boson doesn't exist, the probability of obtaining those kind of results would be at least 5 standard deviations from what we would expect if this boson did not appear. So if we take the Chebyshev inequality and we have 5 sigma event, then the probability of getting that is 1/25. So there's a 4% chance of getting that kind of situation if you use the Chebyshev's inequality. So this doesn't give a very accurate, a very optimistic view of how likely those things are. So let's take another example. The male human height in Finland is roughly, I think it's a bit under 180 centimeters, maybe 178 centimeters. And the standard deviation of that is roughly equal to, I think, 5 centimeters or something like this. It's somewhere over there, or 4 centimeters. Okay. So let's assume nothing about this distribution. So we have this 170. Let's say it's 178 and 5 are those numbers. They could be anything, but there's somewhere along that line. So what is a 5 sigma event in this situation? It's 25 centimeters. So that's 2 times, that's 25 plus 178, that's 203 centimeters. So this gives us that at most 1 in 25 person is a male person is over 203 centimeters. I guarantee you it's far smaller than that. So this is a pessimistic view on that and I actually suspect that the standard deviation is 4 centimeters more likely. So if it's 4 centimeters, then or something like this, but even if it's 5 and 6 sigma event, that would be 208, 7 sigma, well, 10 sigma event would be half a meter. So that would be 230 228 centimeters. Do you think 1% of people are taller than 228 centimeters? I think not. I don't think you do either. What does it say? It doesn't say that that's so. It says that it cannot be more if the variance and the expected value are known like this. This proof is done by approximating upwards. So when we look at this probability that x minus mu is greater than or equal to t. So what we are doing is we are finding the integral of f of x over this region where x minus mu is actually greater than or equal to t, or its absolute value is. Now, think about it this way. In here, I'm going to annotate a little bit. In this proof, I think it's a nice proof. We can think of this as 1 times f of x. And now what is this? Because t is smaller than or equal to x minus mu's absolute value, then this quantity here is at least 1, right? So this latter part is greater than or equal to the first part. Now we can take this 1 over t squared as a coefficient in front, and look at here. This is exactly the thing that we are integrating over when we are calculating the variance. but we are not integrating over the whole region in this situation. But when we integrate over the whole region, we get something that is definitely bigger than this. So it has an upper limit, which is this. But in this case, this integral part here is simply the formula for the variance. So we get that this probability is smaller than or equal to variance over t squared. So this is a simple proof, a very pessimistic one at that, because this part where x minus mu is greater than or equal to t, this is definitely not going to be all of the region. So this is definitely going to be far bigger than that. It is of course possible that the region at the center, think about this distribution. Let me draw you a picture. So we have this distribution, and let's say here is our expected value. That's the mu. So it's possible that the distribution looks like this. This center here is completely empty. But if we put most of the probability mass out here far away, then also the variance tends to be big. So, this is why this happens. Okay. Here's an example. A ball bearing has a diameter of x millimeters. Expected value and density function are unknown. Let me see if there's there's no. But variance is known to be 0.09 millimeters squared. Of course, this is squared because the variance is a square of something. Randomly chosen ball will have a diameter more than 0.7 millimeters off of the expected value, with at most sigma squared over 0.7 milli squared. And we can calculate this. So the thing is, if we know an estimate of the variance, we can get an idea of what is the expected value of getting a very large deviation from the expected value. And the Chebyshev inequality gives the most pessimistic view. I mean, it's definitely mathematically impossible to be more probable to get those extreme values than with the Chebyshev inequality. But for most distributions, it's so pessimistic that it's virtually of no use. So in the exercises, I will put some questions in which you are to compare a certain distribution, and then you know the distribution, you calculate the probability, and then calculate the probability of the same event using Chebyshev inequality. For instance, in the normal distribution, which we will learn shortly, not today, but next week, in the normal distribution, the 5 sigma event is very rare. It's one in several millions. It's one in millions. I think could be even trillions. I'm not sure. 5 sigma, I don't remember exactly, but it's very, very rare. Whereas with the Chebyshev inequality, the 5 sigma event looks like it's 1 in 25. So it could be as bad as 1 or as common as 1 in 25. So really, it's really important to understand the nature and the difference of different kinds of distributions. One of the reasons why I teach you this at this point is that when we later talk about things under the assumption that we have the normal distribution or some other known distribution, and I will give you good reasons to believe that the distributions are all but normal, at least look pretty much like normal distributions. It should be taken as a warning that this is not necessarily always true. I'm going to skip most of this 3.5 where we talk about moment generating functions. These are probability theory that is highly fascinating, These are generalizations of two things. The physical interpretation can be thought of as, center of mass, moment of inertia, and so forth. And another one is Laplace transform for probability distributions. So I'm not going to be talking about this in great detail, and definitely not going to ask this in the exam. But this is a theoretical tool where we can do some tricks, or not tricks, but do a transformation on the random variables density function or something like this, and have an alternative representation for the function, not the density function, sorry, for the random variable, not the density function, but the moment generating functions. And we can think of this is, those of you who know Laplace transforms or Fourier analysis and things like this, there are these transformations which we can do on functions to make it easier, to make them more susceptible for certain kinds of analysis. Reveal things that not immediately obvious in the time domain of signals, or in the whatever domain it is that we are looking at the function. And this can be thought of, these moment generating functions can be thought of as we taking the distribution's density function, which is in the sample space domain, and transforming it into the moment domain, and moments being shape parameter domain, kind of. So we have expected value, we have variance, we have higher momentums which describe, progressively give more weight to those more distant events, distant from the expected value. Skewness, like things like, is it more bulged on the other side? Is it tilted? Is there more ripples on the other side, and so forth? So skewness, kurtosis, and these are names for these higher moments, known as higher moments about the mean. We usually normalize the random variable, and center it around the mean or the expected value. You can think about this expected value. I mean, the only two things that you need to remember are that expected value can be thought of as the first moment around the origin, and that corresponds to the center of mass if you think in terms of physical density, or just expected average value when you do a scatter diagram, the average value of that, and variance can be thought of as, okay, we know the center there, and we center there, and then we look at the moment of inertia of around that point. And then the higher moments are like skewness. Is it skewed on the other side, or does it have a long wiggly tail, and so forth? So these are the sorts of things that we can use to describe the distribution more closely. But as this course progresses, we don't need these so much. So I'm just going to skim through this and try to give you an idea what this is about. Firstly, not all of these quantities exist for all kinds of distributions. So much like in Laplace transformations and Fourier transformations, you don't have necessarily a region of convergence for that. So you have certain kind of functions to be able to have this transformation and converge. So the moment generating function can be thought of as, we take a transformation where we take the expected value of an exponential version of the original random variable. So the random variable is x. We define the moment generating function mt as the expected value of e to the tx. For discrete variable, this can be calculated with a summation. So those of you who are familiar with signal transformations, like using Laplace transformation or the Z transform, these are highly similar to those. Obviously, because M0 is always defined because this density function's always, it's always 1, right? You can see that if we set t equal to 0, then this is always 1. So it has a region of convergence, but for higher values of t, this doesn't necessarily exist. The thing is, why this is important is that if two random variables have the same sample space and they have the same moment generating functions on some interval that contains 0, then the distributions are the same. We don't prove this theorem, but it's like, you can think of this as Laplace transform for distributions. The proof is completely analogous. How do you pronounce that? Well, anyways, it's completely analogous to the proof that uses Laplace transforms and shows that if the Laplace transform is in some non-trivial region of convergence, is the same for these functions. These functions are the same except for a set of measure 0 or something like this. And the moment generating functions can be obtained by, it kind of transforms this idea that if you know the moment generating function, then calculating the expected values, variances, and so forth can be reduced to calculating the moment generating functions, different derivatives. So the first derivative of the moment generating function at the origin is in fact the expected value. The second derivative is the expected value of the square, so you can get it by use of the second derivative and the square of the first derivative and so forth. And the idea, we're not going to be using these extensively, but the idea here is that probability theory can benefit from the same engineering calculus techniques as basically any other theory that makes do with certain kind of functions. And these are definitely L2 functions, meaning that they're integrals over the whole real value plane, and even the square of that usually exists. So this is perfect. These are pretty good candidates for this kind of analysis. We'll see examples where exact expected value might not exist, but it doesn't really matter. We can, for most of the situations, for most of the distributions, these will behave nicely. Not going to go in depth in here, so I just mentioned this as a theory that can be used. All right. Sadly, this section 3 didn't have a material for group work, so I'm going to have a little break here now. I need to drink something to get my throat, dryness off my throat. We'll continue in about 5 minutes, okay? I'll stop the recording for that time. So in this section, we will talk about certain particular distributions. So we now have some theory about how to figure out things about random variable, like in theory. So we'll be putting a little bit more meat on the bones, so to speak, here. We'll be putting some more ideas about how to operate with certain distributions, and we'll come up with an idea of how to just a second, the dog is doing mischief, yeah. So we study the random variable in many ways. Usually we assume that there's experiments and we repeat them multiple times. We may have some other reasons. We may be able to study some kind of origin for this random process, and we can make assumptions and then come up with the model. And let's say that we have some experimental values of your random variable x, and then maybe some assumptions about the nature of the distribution. We can draw conclusions about the probabilities of different events in the sample space. So one common way of doing this is looking at frequency distributions. So we carry out certain experiments, and we look at how often do certain values appear and divide those by the number of observations we made. So if we take an event xi and it occurs fi times in n observations, so we come up with this relative frequency pi is fi over n. So let's say that, for instance, let's say that we say that a person is tall if they are over 188 centimeters tall. So they're 10 centimeters taller than the average person, a male person in this case. And we say that they are tall if this happens, and we just take 100 people and see how many of them are tall. If 12 of them are tall, then we assume that the relative frequency of tallness is 0.12. So given a random variable and a sample, so this we do n repetitions of the random experiment, we get a sample of n values, and we define the sample mean as simply the average value, 1 over n times the sum of xi. So we call, let's say if we take that 100 persons, we look at how tall they are, and we calculate the average height of people in this sample, and that's our sample mean, our sample average also.
I have a question.
Yeah.
What the difference between expected value and sample mean?
Okay, the expected value is a theoretical concept that is related to the model by which we model this this random phenomenon. So, for instance, we can assume, let's say we have some kind of an idea of normal distribution, which you haven't learned yet, but it doesn't matter. Let's say we have some model of what we assume that people's height is. And let's say that has expected value, let's say 178 centimeters. That is the expected value, and it's a purely theoretical concept, one that we usually assume, and we come up with a mathematical guess or model of how height is distributed. The sample mean, on the other hand, is the real life version that should be, if our model is correct, should be pretty close to the expected value, but of course it's a random occurrence in any case. I mean, we take people with random n people, and if n is small, let's say it's 10 people. And if we take 10 people who happen to be players in a basketball team versus 10 people who are, let's say, I don't know, what would be a sport where people are gymnasts, Olympic gymnasts are usually not very tall, then usually we'll get a very different result with this sample mean. So our sample mean is not a theoretical concept. It's a concrete manifestation of us measuring the variable n times and calculating the average. Whereas the expected value is a purely theoretical concept that spawns from the model that we kind of assume or want to apply to the real world. Similarly, sample variance, we can add those numbers together, see how far from the average they fall, calculate the square of that, and divide by n minus 1. And if this n minus 1, why do we divide by n minus 1 and not n? I'll explain it to you shortly. We call this the sample variance. And again, the sample variance is something that if we have a model and the model is pretty much correct, then the sample variance will be pretty much close to the variance of the actual random variable. Now, here was a question, can you please explain why it's n minus 1 and not n? Well, the reason is relatively simple. it's there to point out that it makes no sense, for instance, if we make one sample. Think about the case where we just have one sample. Obviously, that one sample is not a very good or accurate representation of expected value, but it still makes sense to have that one variable and its value is going to be 1, you know, whatever that result is. We may take one person, measure their height, and we guess that, okay, people in this country tend to be this tall. So unless if we pick a random person, it's actually quite probable that they're pretty close to the average person's height. But there is no way in which we can come up with this idea of what the variance is. So let's measure a second one. So we take 2 people at random. Again, the average of their height is now a slightly better approximation of how tall on average people are. That's at least in this country or this region where we are doing this. What is the variance then? Well, let's think about this. There are 2 ways in which we can do it. Well, we calculate the average, but if we divide it by 2 instead of 1, the average distance, and we're actually getting, it's a bit hard to explain, but we will actually be getting a value that is a gross underestimate of the variance, because the average will be somewhere between these 2, but these 2 could be both high or both low values. So it's not very reliable. Okay, let's take 3 then, because with 2 values, it's not very good. So we take 3 values, and let's assume, for argument's sake, let's assume that one of these persons is exactly of average height. That person's contribution to this S2 in this sum here will be exactly 0. But we have these 2 persons who are somewhere other than the average. So we take how far are they from that, take the square, and then take basically the average of that square. This is there to offset the fact, I mean, you know, getting more into the algebraic details of this n-1 here is there to offset the fact that this average here already contains information about all of those, partial information about all of those. So this is why we need something called the degrees of freedom. This eats 1 degree of freedom because it's the sum of all of these already divided by n. And then when we take these deviations, we're going to be dividing by n-1. It's a little bit hard to explain, but I'll show you shortly that we need this formula to prove a certain thing. It turns out that if we divide it by n, we get an underestimate of the variance. And with this n, we can prove that this sample variance defined in this way, when n grows large, it has an expected value. This converges towards the actual variance in that case. And it's going to be a very good approximation actually when n is at least relatively large. We'll cross that bridge shortly. So the thing to notice is here that the sample deviation describes the average distance from the mean in some ways. It's not actually the average distance, but it's a slightly fixed version of the average distance. You cannot express things with these numbers that are such that skewness or asymmetries. So for instance, if we have I'm going to draw another picture. So if we have something like, if we have a distribution that looks something like this, here is the sample mean, or here's the expected value. So we cannot capture the idea that there is a skewness, so that there's a sharp decline on this side and a longer tail on this side. We cannot capture this idea in these numbers. So you have to understand that these two numbers describe can have the ability to describe our distribution only with respect to where the average is and how wide it is. But you know, if it's asymmetric or something, that's something that is not going to be seen in these numbers. We can use these frequencies associated with these xi. So we can calculate these with, I'm not going to skip these frequencies. Let's take an example. Assume that we have 100 measurements, and there's a lot of numbers here, so I'm not going to, of course we don't read them, but let's say that we get this sequence of numbers. We have a component that is used in a factory, and it is installed in a machine, and then every now and then you have to fix it and change it. And let's say all over the world we have different factories where this component is used, and we measure how many years it takes before we are going to have to replace it. And let's say we have these observations. There are small numbers like 0.12 and 0.24, and then relatively small numbers. And then there are relatively large numbers like 6.4 or 7.8 even, in which cases the component has lasted for a long while. So let's say that we classify these into categories so that it's between n and n plus 1. So where n is a non-negative integer, and because no value greater than 8 appears here, so we stop this at 8. So we notice that 39 of these numbers, these 100 components, 39 of these components were replaced within the first year, 21 in the second year, 18 during the third year, 6 in the fourth, 7 in the fifth, 3 in the sixth, and only 1 managed to survive until the eighth year. Cumulative distributions can be obtained from here. Obviously, the assessment of probabilities, this can be thought of. These are not the same as probabilities, but under the frequentist approach, we can think that we get an idea, or we get an estimate, if you will, that the probability that it breaks down, the component breaks down during the first year is somewhere close to or somewhere about 39%. Of course, these numbers at the higher end especially are so small that they're not really very reliable. But we get this idea, this is our estimate, or this is our clue about how they are distributed. If we took this 10,000 experiments or 100,000 experiments, then we'd probably see numbers that are somewhat different in this PI column, which is basically this PI column is basically the probability. If we take the frequentist approach, then that column would start to resemble the probability that component needs to be replaced during that year. And they would be similar to these numbers, but not necessarily quite equal to these numbers. We can draw a histogram here. This is very common. We draw a visualization. So we start to see the pattern of emerging, of the sort of lifespan of these components. Again, if we had a higher n here, we would probably see maybe a smoother, or maybe it would turn out that there's like this bump in there somewhere. We could also, alternatively, we could divide this into half-year intervals. So these columns would be lower, and there'd be more probably noise here and so forth. So we can do lots of these things. We'll look into all of these ideas about statistical inference from data. So in our previous example, the sample average would be roughly 2, namely 1.99, and the sample deviation, or sample variation, sorry, would be 3.18. And you can do this with MATLAB or R. We'll be using MATLAB so that you can calculate it by just creating a vector of all these values and then simply calculating the mean of that. So yeah. So I'm going to stop here for a second. Let's do this as I'm going to resume recording. So like I said here, I just copy pasted it, the X here and calculated the mean and the variance. All right. Let's get back to the material. I'm not going to spend time on doing this histogram. There are tools that you can do. Play around with it. There's an online version of MATLAB as well. Play around with it a little bit. So you can basically just copy paste this and see if you can come up with this histogram computation there. It's not necessary, it's not needed. I'm not going to ask you to submit any pictures like this in the exam or in the exercise. It's just for your benefit. You know, I urge you guys to learn to use the software a little bit. If you're using R, even if you're using Python and some data analysis package, that's fine. Anything that you can use to calculate the mean values and variances. We'll see some statistical testing, so that's about as far as we'll do. I'll show you all that later, how that's done. All right, so now that we have this idea of what these sample things are, so let's get back to these actual distributions, and I'll cover that bridge between sample variance, expected value, and sample mean. We'll cover that towards the next section. So let's look at first some important distributions. The most important, not the most important, the simplest. Okay, let's say it this way. It's not necessarily the most important, but it's the most common experiment that we discuss. It's called the Bernoulli experiment. It's an experiment that has either a success or a failure. So it's basically a coin toss or some other thing that results in either a yes or a no, or a 0 or a 1. And we have some probability thereof. So the Bernoulli distribution is the simplest distribution there is. The sample space consists of two values, 0 and 1, and the density function has values p and 1p, 1 minus p. So this is the Bernoulli distribution. So if you read a paper that says, oh, we are assuming that this certain sort of phenomenon follows the Bernoulli distribution, well, basically it's a possibly skewed coin toss, right? It's nothing else. And if you don't take anything other than from this course or anything else from looking into the probabilities and data analysis, then understand that Bernoulli distributions can be different depending on what that P is. I know I shouldn't maybe talk about this, but you know, I can't help myself. So very often the case is you see this like, okay, you take the vaccine for some disease and it doesn't provide you with 100% protection. So you may still contract the disease, but you know, the probability is different. So when you go out, and participate in whatever it is that you participate in, you're kind of doing a Bernoulli experiment, whether or not you will contract this illness. So if you have a vaccination, then you're dealing with a different Bernoulli distribution than you were without it. So the P is different. But there are tons of people who say it's still a coin toss, so it's 50-50 because it either happens or doesn't. This portrays a fundamental lack of understanding of how probabilities work. And I hope that at least this particular lack of understanding or this lack of this particular misconception has been dispelled. If the probability is different, then it's a different distribution, so it's not all the same. Okay? So in any case, Bernoulli experiment is basically the simplest possible experiment, and the related Bernoulli distribution is probably the simplest possible distribution. We're not actually interested in the Bernoulli distribution. Instead, we are deriving other distributions from this Bernoulli experiment. Assume that we repeat the Bernoulli experiment n times so that all these experiments are independent. Think we tossed a coin n times, or think we go to the grocery store, we go to the supermarket, we go to the movies, we go to somewhere, I don't know. And let's assume that every time we have the same probability, which is not necessarily the case, but let's say that every time we do something like this, we get the same probability of contracting the illness. So we can have a distribution for this, in which case it depends on n. I don't think this is a very good example, because we in this disease example, or this illness example, we either get it or don't. So let's assume that, let's say that we are a bird watcher person. And every time we go out, we mark an X in our notebook if we see a certain bird. There's a low chance of that happening. But if we go out n times, then we have a chance of seeing it between 0 and n times. And assuming that it's the same Bernoulli experiment every time, we have a sample space which is discrete, values between 0 and n. The actual results of this experiment has 2 to the n possible outcomes, because it's either a 0 or 1 at each of these possible experiments. So there's 2 to the n possibilities, but if we are only interested in how many times it was 1, then we have to calculate the probability of getting, we have to calculate the distribution for this new sum of ones variable. And the probability for a particular result, if we have x successes, is p to the x times 1 minus p to the n minus x. Because if we do it n times, then x of these are successes, that's p to the x, and 1 minus p of these are failures, that's 1 minus p to the n minus x, because n minus x are failures. So how many ways in which this x successes out of n can come from? That's n choose x. So the probability that we get as our repeated experiment, we get x successes, is n choose x times p to the power of x times 1 minus p to the power of n minus x. And this is called the binomial distribution with the parameters. It has 2 parameters, the n and the p. So the binomial distribution is derived from a repeated Bernoulli experiment where we calculate the number of successes. And each Bernoulli experiment has the same, it has to have the same probability p, and we repeat it n times. Then we say that this x is binomially distributed, or it follows the binomial distribution with parameters n and p. And the sample space is between 0 and n, and the density function is this n choose x times p to the x times 1 minus p to the n minus x. This should be known to you from previous courses, but just to recap. We can verify that this is a legitimate density function. It's non-negative, and using the binomial formula, we can prove that the sum of these is 1. There's a moment generating function which we can use here. I'm not going to assume that you use the no moment generating function, but it's actually very nice. If we have this moment generating function, then the variance and the expected value are actually fairly easy to calculate. Otherwise, they're not, because the sum, the expected value is relatively tricky, and so is the variance. So I'm not expecting you guys to be able to derive the expected value of the binomial distribution. You can just memorize it, basically. It's got expected value n times p, which doesn't seem all that surprising, because if you think about it, you do n times an experiment, each of these has p probability of being successful, so n times p is the expected value of successes. It's not that hard. That's true. The variance, on the other hand, is n times p minus 1. So we see, again, this is derived using the moment generating function. I'm not going to go through this proof here, but the interpretation of this variance is that the variance is bigger when p is close to 0.5. And it's smaller when p is either very close to 1 or very close to 0. Then the variance is small. Here's an example. Regular coin is tossed 5 times. The number of heads is a variable x, and it has this distribution 5 choose x times 0.5 to the 5. The manufacturer has 5% faults in the transistors. So this is an example. This is something that you might want to do. So I'm going to use the group work session here. So the setup of this is that a manufacturer has 5% of their transistors turn out faulty. A customer buys 6 transistors. Assume that this is a binomial distribution. Let x be the random variable that describes the number of faulty transistors in this purchase. Calculate the probability that 1 or 2 of these are faulty, and calculate the probability that at least 1 transistor is faulty. I'm going to pause